In the 21st century, China, having healed from the wounds of the Century of Humiliation, has displayed engineering feats that leave even the world's most developed countries in awe. Former US President Donald Trump once openly admitted that America could never compete with China's infrastructure, marveling at its roads, bridges, and cutting-edge construction projects. But does the reality truly match this praise? Is China genuinely outpacing the West in technological ingenuity, or is this an illusion shaped by grandeur? Well, seeing is believing, they say. Today, we'll take a look at how China's insane construction tech has created the world's longest underwater tunnel. This is one story you would not want to miss. Hang around and you'll surely be impressed. The Shenzhen-Zhongshan Link. While there is no shortage of examples when it comes to China's supremacy in the arena of erecting monumental infrastructure, the Shenzhen-Zhongshan Link is particularly notable because it boasts an unparalleled scale of ambition in its category, and it is an ongoing effort which makes it a soon-to-be historical endeavor. Designed as a critical transportation artery in the Guangdong, Hong Kong, Macau Greater Bay Area, this 24-kilometer megastructure seamlessly integrates bridges, artificial islands, underwater tunnels, and even a pioneering submarine interchange. As one of the most ambitious cross-sea transportation projects in history, it not only shortens the travel time between the economic hubs of Shenzhen and Zhongshan, but also showcases China's infrastructure innovation. So, how come China can invest so much and innovate so elegantly in infrastructure? Well, let's find out with this case study. At its core, the Shenzhen-Zhongshan Link is designed to alleviate congestion and create a direct link between Shenzhen, a global tech powerhouse, and Zhongshan, a key manufacturing and trade hub. Often called China's Silicon Valley, Shenzhen is a global leader in technology, finance, and high-end manufacturing. What was once a small fishing village has grown into a megacity of over 17 million people, driving China's rapid economic rise. Home to giants like Huawei, Tencent, DJI, and BYD, it has become a world-class hub for telecommunications, artificial intelligence, and hardware innovation. Beyond tech, Shenzhen is also a financial powerhouse, housing the Shenzhen Stock Exchange and a booming fintech sector. As a key player in international trade, its ports process massive cargo volumes, making it a crucial link in the global supply chain. With its fast-paced economy and relentless innovation, Shenzhen's need for efficient transportation networks has never been greater. Zhongshan, located on the western bank of the Pearl River Delta, plays an equally vital role in China's industrial landscape. While Shenzhen thrives on high-tech industries, Zhongshan is a key manufacturing and trade hub specializing in machinery, home appliances, and precision equipment. The city is home to over 30,000 industrial enterprises, many of which are deeply integrated into global supply chains. As a part of the Greater Bay Area initiative, Zhongshan is rapidly modernizing, attracting new businesses and infrastructure investments. However, connectivity with Shenzhen has long been a challenge. Before the Shenzhen-Zhongshan Link, the only major connection between these two economic powerhouses was through the Human Bridge, or ferries, both of which were heavily congested. The current travel time of 2 to 3 hours creates logistical bottlenecks for businesses and delays for commuters. The Shenzhen-Zhongshan Link cuts this travel time to just 30 minutes, revolutionizing the flow of commerce, reducing transportation costs, and further integrating the region into a seamless economic corridor. By eliminating these barriers, the link is set to enhance productivity, attract more investment, and solidify the Greater Bay Area as a global economic powerhouse. The sheer scale and complexity of the project are unmatched. The Shenzhen-Zhongshan Link consists of a 17-kilometer bridge system that extends across the Pearl River estuary, punctuated by 2 massive artificial islands that serve as key transition points. From there, the structure plunges into a 6.8-kilometer underwater tunnel, making it one of the longest and most advanced immersed tunnels in the world. What sets this tunnel apart is the integration of a submarine interchange, a groundbreaking engineering feat that allows vehicles to seamlessly shift routes underwater. This is a first of its kind in large-scale civil engineering. The construction of the Shenzhen-Zhongshan link demanded some of the most advanced engineering solutions ever deployed in infrastructure development. The underwater tunnel, for instance, consists of 32 massive prefabricated concrete segments, each weighing over 80,000 tons, carefully submerged and aligned on the seabed with millimeter precision. Specially designed seismic-resistant technology ensures the structure remains intact even under extreme environmental stress, including typhoons, strong tides, and potential seismic activity, all of which are ever present in the Pearl River Delta. Furthermore, the artificial islands are designed to support additional facilities, such as emergency response centers, toll stations, and logistics hubs, further enhancing the strategic value of the link. Sustainability has also been a major consideration, with noise reduction materials and environmental protection measures integrated into the construction process to minimize the ecological impact on the Pearl River estuary's fragile marine ecosystem. The Shenzhen-Zhongshan link represents China's ability to push the boundaries of engineering, integrating cutting-edge technology, sustainability, and urban planning into a single megastructure. Let's break it down piece by piece. The undersea tunnel, a technological breakthrough. The undersea tunnel of the Shenzhen-Zhongshan link is a technological marvel, redefining the limits of marine engineering and tunnel construction. Stretching an impressive 6.8 kilometers beneath the Pearl River estuary and buried at depths of over 40 meters, this submerged passage is one of the most ambitious underwater infrastructure projects ever attempted. Designed with 8 lanes per direction, it far surpasses the capacity of the Hong Kong-Zhuhai-Macau tunnel. The sheer scale of the tunnel is matched only by the complexity of its construction. As noted earlier, the Shenzhen-Zhongshan link's undersea tunnel was built using the immersed tube method, where 32 enormous prefabricated segments, each weighing over 80,000 tons, were carefully floated, submerged, and joined on the seabed with millimeter precision. This may sound simple, but it is far from it. You see, the challenge was to ensure airtight connections between segments in the high-pressure underwater environment while maintaining the tunnel's ability to withstand extreme conditions, including seismic activity, typhoons, and strong tidal currents. Creating such airtight connections between segments in an undersea tunnel is one of the most formidable engineering challenges, particularly in a high-pressure marine environment where structural integrity is constantly tested by extreme forces. One of the biggest concerns was water infiltration, as even a minor leak could compromise the tunnel's long-term durability. Engineers tackled this by designing precision-machined steel gaskets combined with high-performance elastic sealing materials, ensuring a vacuum-tight seal between segments. Each segment, measuring 55 meters long, 46 meters wide, and 10.6 meters high, was meticulously aligned using a floating docking system with a 2 mm margin of error, significantly surpassing conventional tunnel construction standards. Another major challenge was seismic resilience, given that the Pearl River Delta is prone to geological activity. Traditional expansion joints are vulnerable in such environments, but the Shenzhen-Zhongshan link's engineers introduced high-flexibility seismic-resistant expansion joints that allow the structure to absorb and dissipate seismic energy, significantly reducing the impact on aquatic ecosystems compared to similar projects like the Hong Kong-Zhuhai-Macau Bridge. Air quality and ventilation were also key concerns, given the tunnel's 8-lane bidirectional layout and expected daily traffic exceeding 100,000 vehicles. To combat air stagnation and carbon buildup, the tunnel features a multi-stage air purification and ventilation system with high-efficiency particulate air, or HEPA, filters and real-time carbon dioxide monitoring sensors. These filters capture over 90% of fine particulate matter, ensuring that air quality inside the tunnel remains comparable to ambient outdoor air. by integrating a longitudinal airflow management system. Engineers also prevent vehicle emissions from accumulating in certain zones. Another critical safety innovation is the adaptive LED lighting system, designed to improve visibility while reducing driver fatigue. Unlike traditional tunnel lighting, which can cause abrupt brightness shifts when entering or exiting, this system gradually adjusts illumination levels based on vehicle speed, time of day, and weather conditions. Research from similar tunnel projects indicates that adaptive lighting can reduce accident rates by 30%, as it minimizes sudden changes in light exposure that often lead to temporary visual impairment. Additionally, the LEDs are energy efficient and low heat emitting, cutting power consumption by 40% compared to conventional high-pressure sodium lamps, while ensuring a consistent and glare-free driving experience. This undersea tunnel goes beyond just being a transportation marvel. It reflects China's commitment to green, intelligent, and future-proof engineering. And this is just one segment of this impressive megastructure project. However, making it possible was not simple. Challenges and innovations in tunnel construction. The construction of the Shenzhen-Zhongshan undersea tunnel was a bold defiance of Western skepticism. When China first announced its plan to build an 8-lane bidirectional tunnel under the Pearl River estuary, Dutch and other Western engineers questioned its feasibility, arguing that the sheer size and weight of such a structure would make it impossible to maintain long-term stability. They pointed out that each additional lane would increase hydrostatic pressure by 27%, meaning that an 8-lane tunnel would experience exponentially greater stress than any previously built immersed tunnel. Additionally, the tunnel would sit beneath one of the busiest shipping routes in the world, with 10,000-ton cargo vessels routinely passing above. The risk of structural failure under these immense loads was a critical challenge. Such a challenge had never been tackled at this scale. At a depth of over 40 meters, the tunnel is subjected to enormous hydrostatic pressure, far beyond what is typically encountered in submerged tunnels. With every lane added, the pressure increases by roughly 20,000 metric tons, meaning that traditional tunnel materials would struggle to maintain their integrity over decades of use. The challenge was not just about building a large tunnel, it was about creating a structure that could resist immense water pressure, ship-induced vibrations, and shifting seabed conditions, all while ensuring long-term durability and minimal maintenance. To overcome these challenges, Chinese engineers had to reinvent tunnel construction from the ground up. Instead of relying on traditional reinforced concrete, which would have been prone to cracking under extreme pressure, these joints can handle lateral movements of up to 300 millimeters, reducing stress on the tunnel walls and preventing structural failure during an earthquake. This level of resilience surpasses the standards set by the Tokyo Bay Aqua Line, which also operates in a seismically active zone but features expansion joints with a smaller tolerance. To counteract buoyancy forces, engineers implemented an anti-buoyancy foundation system, using a combination of deep-sea anchor piles and ultra-dense reinforced concrete. Given that each submerged segment weighs more than 80,000 tons, keeping them stable without external displacement was critical. Compared to the Hong Kong-Zhuhai-Macau Bridge undersea tunnel, where anti-buoyancy was managed with traditional ballast systems, the Shenzhen-Zhongshan Links approach provides 40% greater stability against shifting seabed conditions. Moreover, the estuary experiences some of China's strongest tidal currents, with speeds reaching 2.5 meters per second. To protect the tunnel from erosion and shifting seabed conditions, engineers used an advanced sediment stabilization system, integrating reinforced geotextile layers and dynamically adaptive breakwaters. This ensures that underwater currents do not gradually weaken the tunnel's foundation over time, a common issue in submerged infrastructure projects like the Öresund Bridge tunnel between Denmark and Sweden. What truly sets this tunnel apart, however, is its unprecedented technological sophistication. At its core lies a groundbreaking smart monitoring system, integrating 23,000 fiber optic sensors directly into the tunnel's concrete structure. These sensors provide real-time stress, strain, and temperature data, allowing engineers to detect microfractures, monitor load distribution, and predict structural fatigue before it becomes a safety risk. This level of continuous automated health monitoring is a first for undersea tunnel construction and enhances long-term durability by enabling preemptive maintenance before major issues arise. The precision and sensitivity of this monitoring system are unparalleled. The fiber optic sensors embedded within the tunnel boast a 40% higher sensitivity than comparable systems used in the West. This allows for more accurate and immediate data collection, effectively making the concrete think. This feat is so revolutionary that it was recognized by the prestigious journal Nature. The integration of smart sensing technology into traditional concrete structures transforms the tunnel from a static passageway into a self-diagnosing, self-reporting structure, significantly reducing maintenance costs and extending its lifespan. Beyond its sheer scale and technological breakthroughs, the Shenzhen-Zhongshan undersea tunnel also sets a new benchmark in environmental protection and human safety. Given the ecological sensitivity of the Pearl River estuary, home to diverse marine life, including the endangered Chinese white dolphin, engineers implemented low-noise construction techniques to minimize underwater sound pollution. Instead of conventional pile-driving methods, which produce disruptive shockwaves, they used vibration-reducing hydraulic jacks and bubble curtain technology, which absorbs and dissipates noise before it reaches marine species. These measures helped cut underwater noise pollution by up to 60%. They pioneered a steel-concrete composite structure. This innovation combined the best of both worlds. The steel shell provided superior tensile strength and flexibility, preventing cracks from propagating through the structure, and the concrete core enhanced compression resistance, ensuring the tunnel could withstand the staggering weight of ocean water above. This combination resulted in a 400% increase in flexural rigidity, meaning the tunnel was 4 times more resistant to bending and deformation compared to conventional designs. This steel shell concrete structure was a complete reimagining of how undersea tunnels are built. Traditional reinforced concrete requires extensive manual labor, making large-scale projects more time-consuming and error-prone. The new steel-concrete hybrid design dramatically reduced labor intensity, allowing prefabricated segments to be built with millimeter precision before being submerged and connected on the seafloor. This breakthrough did more than silence skeptics. It set a new benchmark for tunnel engineering worldwide by demonstrating that an 8-lane bidirectional undersea tunnel was not only feasible, but structurally superior to previous designs. China effectively rewrote the rules of large-scale marine infrastructure. This tunnel doesn't just connect 2 cities. It ushers in a new era of supermassive underwater infrastructure. To get a better sense of how impressive this tunnel is, we need to take a look at the tunnel's precision parameters. Precision manufacturing and assembly. The Shenzhen-Zhongshan undersea tunnel is a masterclass in precision manufacturing and automated assembly, pushing the boundaries of what is possible in subsea infrastructure. Traditional tunnel construction often relies heavily on manual labor, but for a project of this magnitude, even microscopic deviations in construction could lead to structural weaknesses over time. To ensure unmatched durability and precision, China implemented an automated production process that surpassed even the most rigorous international engineering standards. At the heart of this operation was a highly automated production line, where steel plates were precision cut and robotically welded with an accuracy level never before achieved in immersed tunnel construction. The welding accuracy of 0.02 millimeters exceeded the German DIN 6700 standards, which are one of the world's most stringent quality benchmarks, by an astonishing 22%. This was a major breakthrough, as even a 0.1 millimeter deviation in tunnel segments could create misalignments that would compromise the structural integrity of the entire tunnel over time. To achieve this ultra-high precision, engineers employed laser-guided cutting systems to ensure millimeter-perfect steel plate dimensions. They also put to use automated robotic welding arms, capable of applying consistent, high-strength welds without human error. Real-time AI monitoring systems also detected microscopic inconsistencies, allowing immediate corrections. By eliminating human-induced welding imperfections, this approach dramatically improved the durability of the tunnel, ensuring that it could withstand extreme pressures for decades without significant maintenance. Moreover, given the sheer scale of the tunnel, a single, continuous structure was impractical. Instead, engineers employed a segmented tube construction method, dividing the tunnel into 22 giant prefabricated segments, each weighing tens of thousands of tons. These segments were meticulously constructed off-site under controlled conditions before being transported and assembled underwater. To ensure flawless integration of these massive tunnel sections, the assembly process relied on gantry cranes capable of lifting and positioning entire tunnel segments with sub-millimeter precision. Automated machinery also ensured that each segment was perfectly aligned before being permanently joined. Moreover, vacuum-sealed alignment systems eliminated even the slightest gaps between segments, reducing structural stress points. Each segment had to be airtight and watertight, as even a hairline fracture could allow seawater infiltration, jeopardizing the entire project. To mitigate this risk, engineers used custom-engineered high-pressure gaskets between tunnel sections, ensuring that the connections were as strong as the tunnel walls themselves. The precision achieved in welding, cutting, and assembly has demonstrated that fully automated, AI-driven megaprojects are not just possible, but superior to traditional manual construction methods. In this context, the Shenzhen-Zhongshan link
is a cross-sea passage connecting Shenzhen to Zhongshan in the GBA.
Is a glimpse into the next era of engineering innovation, longevity and corrosion resistance. Built to last 100 years, the Shenzhen-Zhongshan undersea tunnel is designed to endure severe marine conditions, high hydrostatic pressures, and continuous exposure to corrosive seawater. Achieving such an extended lifespan required groundbreaking innovations in corrosion resistance, structural protection, and self-maintenance. One of the greatest challenges of underwater tunnel construction is the constant exposure to saltwater-induced corrosion, which can weaken metal and concrete over time. To counteract this, engineers developed a 5-layer anti-corrosion coating, drawing inspiration from shark skin, a natural surface known for its resistance to microbial growth, self-cleaning properties, and durability. The tunnel's 5-layer anti-corrosion system is a groundbreaking innovation designed to withstand the harsh marine environment and ensure longevity. At its core, the epoxy resin primer forms the first line of defense, creating an initial waterproof seal that prevents moisture from penetrating the structure. This is followed by a polyurethane barrier layer, which is specifically engineered to absorb mechanical stress and prevent cracks caused by temperature fluctuations. To reinforce the surface against abrasion, high-speed tidal currents, and saltwater erosion, engineers incorporated ceramic nanocoating, which significantly enhances durability compared to traditional anti-corrosion treatments. Adding another layer of resilience, the hydrophobic fluoropolymer film repels water and oil, mimicking the natural water-shedding properties of shark skin to reduce long-term material degradation. The most advanced component of this system is the self-healing protective membrane, which uses microcapsule technology to autonomously repair minor scratches, microfractures, and surface wear before they expand into structural vulnerabilities. This biomimetic approach ensures that the tunnel remains highly resistant to rust, salt damage, and structural degradation for at least a century. Despite the anti-corrosion coating, some degree of metal exposure is inevitable, particularly at connection points between tunnel segments. To further mitigate corrosion, engineers installed 552 sacrificial anodes, a well-established technique in marine engineering that prevents electrochemical corrosion. Each anode is composed of high-purity zinc and aluminum alloys, which are more reactive than the steel components of the tunnel. These anodes attract corrosive elements, corroding themselves instead of the tunnel structure, a process known as cathodic protection. The system is monitored in real time, ensuring that depleted anodes are replaced before they lose effectiveness. This dual-layer protection of chemical coatings and sacrificial anodes ensures that no exposed steel in the tunnel is ever at risk of rusting. Moreover, in any marine environment, underwater structures are prone to biofouling, which is the accumulation of algae, barnacles, and bacteria, which can degrade surfaces over time. To combat this, engineers implemented an advanced surface treatment system that provides the tunnel with self-cleaning capabilities. The hydrophobic fluoropolymer layer on the outermost surface prevents organic matter from adhering to the tunnel walls. A low-friction, antimicrobial coating disrupts bacterial growth, preventing biofilm formation. On top of this, electrically charged nano-coatings create a subtle repelling force that deters barnacles and algae from attaching. These technologies ensure that the tunnel remains smooth, clean, and free of biological obstructions, preserving not just its appearance, but more importantly, its structural performance and water resistance. All put together, these protective mechanisms take longevity to a whole new level. Intelligent concrete pouring system. Another area where the Shenzhen-Zhongshan link pushes the boundaries of practicality is concrete engineering. Using cutting-edge robotics, real-time monitoring, and nanotechnology, the project redefines global standards for undersea infrastructure durability and resilience. Traditional concrete pouring methods are time-consuming and prone to human error, leading to uneven density, micro cracks, and structural weaknesses over time. To eliminate these risks, engineers developed a fully automated concrete pouring system, utilizing robotic precision and real-time data analysis. Equipped with 1,200 embedded sensors, these robotic systems monitor flow rate and pressure to ensure consistent material distribution, temperature differentials to prevent thermal cracking, and hydration reactions to optimize curing times. This innovation reduces the traditional 90-day manual pouring and curing process to just 28 days. This is a 68% efficiency increase, minimizing environmental exposure and accelerating project timelines. The use of AI-driven monitoring ensures that the concrete is poured at the exact right consistency and temperature, eliminating air pockets and weak points before they form. A common challenge in large-scale concrete structures is achieving full compaction without structural gaps or voids. Conventional techniques rely on mechanical vibration, which can lead to uneven settling and long-term weakness. Instead, engineers introduced a zero manual vibration system, utilizing self-compacting concrete or SCC with nanometer-level flow control. SCC is engineered to be highly fluid, yet structurally robust, allowing it to flow into every crevice without external force. Its ultra-fine particle composition ensures a 100% seamless bond between segments, reducing the risk of cracks, water seepage, and future deterioration. Moreover, the absence of mechanical vibration eliminates inconsistencies, ensuring that the entire tunnel structure is uniformly strong from the core to the outermost layers. This breakthrough enhances load-bearing capacity, ensuring that the tunnel can withstand immense external pressures, seismic forces, and long-term environmental stresses. But that's not all. A tunnel of this magnitude must withstand some of the harshest environmental conditions on Earth, requiring rigorous durability testing beyond conventional engineering standards. The Shenzhen-Zhongshan link underwent simulated stress tests that measured its resilience against a century of extreme natural disasters. And here, the word extreme is as literal as it can be. For instance, during the 1000 typhoons simulation, engineers subjected the tunnel materials to continuous high-velocity water currents and wind pressure simulations, replicating the destructive forces of 1000 Category 5 typhoons. The self-compacting concrete withstood hydrostatic loads without micro-fractures, proving its ability to survive extreme weather conditions. Then came the Level 9 earthquake resilience simulation. Here, the tunnel structure was tested against intense ground-shaking simulations, mimicking earthquakes stronger than those that devastated Fukushima and Sichuan. The high flexural rigidity of the steel-concrete composite ensured that no structural failure occurred even under severe seismic stress. The 3-meter sea level rise simulation saw engineers modeling future climate scenarios, exposing the tunnel to conditions mimicking a 3-meter rise in global sea levels, which is a worst-case projection for the next 100 years. The tunnel's hydrophobic coatings and reinforced water barriers proved highly effective, ensuring it remained watertight under elevated pressures. These stress tests confirmed that the risk of catastrophic failure was reduced by 83%, far exceeding international safety standards and setting a new benchmark for long-term structural resilience in undersea construction. But that's not all. Smart manufacturing and transport logistics. The success of the Shenzhen-Zhongshan link hinges on China's revolutionary Smart Dream Factory, an AI-driven manufacturing hub, and a massive transport operation that moves 80,000-ton tunnel sections with near-military precision. To meet the immense structural demands of an 8-lane undersea tunnel, engineers turned to a fully automated, AI-controlled prefabrication plant, nicknamed the Smart Dream Factory, where each tunnel segment is built with robotic precision. The prefabrication facility behind the Shenzhen-Zhongshan link operates at an unprecedented level of efficiency, delivering one massive tunnel segment per month. This production rate is 25% faster than previous undersea tunnel projects. This accelerated pace is achieved through a combination of advanced automation, optimized logistics, and precision engineering, ensuring that each segment meets exacting structural standards without compromising on quality. Unlike conventional construction sites that are subject to weather fluctuations and environmental variables, these segments are manufactured in a fully climate-controlled environment where temperature and humidity are meticulously regulated. This precision-controlled process eliminates thermal expansion inconsistencies, premature drying, and micro-cracking, which are common issues in traditional concrete construction. By maintaining a uniform curing environment, engineers ensure that each segment achieves its full compressive strength and structural integrity, reducing the risk of long-term weaknesses that could compromise the tunnel's resilience under high-pressure underwater conditions. Next comes the AI-driven quality control system. Using advanced laser scanners and real-time monitoring systems, engineers measure every tunnel segment with sub-millimeter accuracy, ensuring absolute uniformity across all prefabricated sections. This level of precision is critical for maintaining seamless alignment when assembling the massive 80,000-ton tubes underwater, where even the slightest deviation could compromise structural stability. Robotic arms further enhance this precision by performing ultra-accurate welding and steel reinforcement placement, eliminating inconsistencies that typically arise from human error. Unlike traditional methods that rely on manual inspection and labor-intensive adjustments, the AI-driven system continuously analyzes stress points, detects microfractures, and adjusts fabrication parameters in real time, ensuring that every component meets or exceeds international engineering standards. Once fabricated, each massive tunnel segment must be transported to the construction site. This is a logistical challenge, requiring some of the largest and most advanced transport technology ever deployed. The Chinese have an answer to that as well. Each prefabricated section rests on a custom-built platform fitted with over 1,000 steel wheels, individually calibrated to adjust for terrain shifts and weight distribution. This eliminates stress points that could lead to microfractures during movement, a common issue in large-scale infrastructure projects. Traditionally, moving these enormous structures from the manufacturing site to the installation location took up to 7 days. Engineers revolutionized the process by integrating high-precision GPS tracking and synchronized AI control, allowing for real-time adjustments in positioning and speed. This breakthrough reduced transportation time to just 4 hours, drastically improving efficiency while minimizing risks. Next up, before installation, each tunnel segment undergoes rigorous quality assurance, via millimeter precision, non-destructive testing. This method detects even microscopic flaws in steel and concrete, ensuring the structural integrity of the Shenzhen-Zhongshan Link's undersea tunnel sections required an array of cutting-edge diagnostic technologies to detect even the slightest imperfections before deployment. Engineers used ultrasonic scanning and X-ray imaging to analyze the internal consistency of each section, identifying microscopic weaknesses that could compromise long-term durability. To further safeguard against potential failures, magnetometry tests were conducted to detect imperfections in welding seams, preventing early-stage material degradation that could be exacerbated by constant exposure to seawater and shifting pressures. Beyond structural assessments, engineers subjected each tunnel section to submersion pressure simulations, replicating ocean depth pressures to ensure the sections could endure the immense forces at play once installed. These exhaustive inspections guarantee that each segment meets or exceeds international safety standards, reinforcing the tunnel's 100-year lifespan. The Shenzhen-Zhongshan link clearly reflects China's ability to merge cutting-edge technology with large-scale logistics to create next-generation infrastructure. The Smart Dream Factory's automated precision, groundbreaking transport system, and rigorous quality control showcase how China is pushing the frontiers of mega-project construction. This project is also a new global benchmark, demonstrating how automation, AI, and high-tech logistics can revolutionize infrastructure development. By setting new standards for efficiency, durability, and scale, China is proving that its infrastructure prowess is unmatched. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.